I'm your host, Grayson Brulte. Welcome to another episode of SAE Tomorrow Today, a show about emerging technology and trends in mobility with leaders and innovators to make it all happen. On today's episode, we're absolutely honored to be joined by Alexey Matushev, CEO and co-founder of Natilus. On today's episode, Alexey and I will discuss blended-wing aircraft design and its impact on the air freight market and what happens when blended-wing aircraft design goes into commercial aviation. We hope you enjoy this episode. Alexey, welcome to the podcast.
Thank you so much for having me.
It's great to have you here. I think blended wing design is cool, and I wish more planes, both freight, air, and commercial, would design it, because the efficiencies that blended wing can design, in my opinion, are pretty astronomical, and we'll get into that today. You're focused on the air freight side of the market. How are you currently thinking about the air freight market? Is it looking to increase efficiency? Is it looking to increase the length of the packages can travel? I know that if you look at a very common route, China, Vietnam, India to America, is iPhone, MacBook route. Very expensive. You can't put it on boats because there's bad pirates out there that will love nothing more to take the MacBooks. So how are you thinking about the air freight market?
So I think the air freight market, I guess what we've seen in the industry for, 60 years is that we design essentially airplanes around passengers first. And then, whatever falls out becomes the freighter. And so as we started the company with a focus on air freight, we started to really see this trend where the traditional tube and wing airplanes are cubing out on volume before they top out on weight. And that kind of makes sense. You open up an iPhone, or an Amazon box today, it's actually halfway filled with air. And so what the industry is really looking for is a more volume-centric design. And so the blended wing body is really a great platform for that. And so you're actually able to carry almost 40 to 50% more revenue cargo for the same trip. And so when you think about, dollars per pound of transporting goods on a global level, you mentioned, Asia to United States, you're really able to change the unit economics while still utilizing, same engine technology, but with a unique airframe.
And I'm going to get in the details here, but if you look at, you're on a commercial plane, and I'm curious, I look out the window and you see that they're loading the certain design of the cargo. Does those containers change for the blended wing design? Do you design them with your partners for more efficiency? So if you look at a very large international carrier, for example, a DHL?
Yeah, so there's kind of two ways to think about it. There's the upper deck and the lower deck. There's different contours surrounding different containers within the lower and the upper decks. With the blended wing body, you have a rectangular cross section. So you don't have the weird corners, I would say, that are, the tube and wing configurations are really plagued by. And so you're able to move into more standardized, what we call cookie sheet pallets. So you have essentially an aluminum sheet and boxes stacked on top of it with netting. And those are starting to look rectangular. And so you're actually giving even more efficiency because you don't have those weird contours inside the airplane.
So your design, the blended wing, is 40 to 50% more cargo. While you can do that, do you feel the market's ready for that? Or is the market kind of, we've seen in other markets, it's stuck in its way and it's happy with the inefficiencies?
I don't think any airline right now is happy with sustainable inefficiencies as well operating inefficiencies. Airlines are a very interesting business where their operating margins between 3 to 4%. And so out of the 3 to 4% of revenue cargo or revenue passengers, about 60% of it is tied with fuel. And so when you think about how much cargo you're carrying means how many trips you're going to take, and then you tie it with, of course, the fuel efficiency of the blended wing body. And then the last piece of it is, of course, CO2 and sustainability. I think they're very excited about new products entering the market, considering a lot of the technology that they're currently using is from the 1960s.
I mean, can you imagine if we were using a phone from the 1960s today? We'd be on roto dial, and we still have the individuals that would connect the phones and to be highly inefficient. We wouldn't be having this conversation right now. From a fuel efficiency standpoint, what does blended wing design unlock? Are you able to get a significantly more range? And are you flying at different altitudes than a traditional cargo air freight plane today?
Yeah, so just to kind of set some foundation, what's really unique about the blended wing body design is the way that lift is moved around the airplane. And so as an example, a tube and wing configuration, 90% of the lift is coming in from the wing and 10% from the fuselage. In a blended wing body design, the fuselage, because of its unique shape, is going to be about 40 to 50% lift. And then the wing is actually 50% as well. And so you really design the fuselage shape almost like another wing. And it makes for a very, I would say, challenging engineering problem. But at the same time, if you can get it right, you're really able to move a lot of those efficiencies out, such as reduction in drag, smaller wing, less cross-sectional area.
Then let's get into the tactical aspect that everybody can relate to: runway. Does the runway distance have to change? And there are certain parts of the world where altitude makes a difference of aircraft's landing. Does that play? Does altitude and range of the landing strip have any impact?
It is. So there is a challenge with blended wing bodies on takeoff performance, and specifically, you don't have a tail. And so the wing is producing not only lift on the front side of it, but it's also trying to trim the torque or the pitching moments around the airplane on the backside. So you have to be very careful on how you design it. And so traditional tube and wing airplanes have, I would say, longer field performance. But there's certain things that you can do within the configuration, which will help reduce the airplane's weight, which will then essentially be able to maintain the same field performance. But you're absolutely right. If you think about like Quito is a very interesting airport. I think it's at 10 or 13,000 feet. I mean, it's really a high elevation. And then it also is really hot over there. And so, the aerodynamics of the airplane change on the airframe side, but also most importantly on the engine side. And so those types of airports are very unique study cases with a lot of our customers of can you meet those field performance requirements, and what do you need to do to the airplane to size it to be able to do those things. Thankfully, Quito built a 13,000-foot runway as well. So they essentially solved our problem for us by putting more concrete on the pavement.
Checkbox 1, checkbox 2. Okay, there.
Yeah, exactly.
On the engine point, we have GE engines, we have Rolls-Royce engines, we have various different engine manufacturers. Do you have to have a special type of engine made, or can you use one of the traditional engines that's currently in commercial use today?
I think there's a saying, never put a new engine in a new airframe. And I'm a big believer in that. So there's so much more risk with that. And so we've really spent a lot of time with our customers designing the airplane around the current engine technology. And so, there's, as you said, the GEs, the Rolls-Royces, and the Pratts that really focus on these types of airplanes, depending on which product. And so we work really closely with them to make sure that our weights are consistent with the amount of thrust that they're able to give to us. And on the flip side, too, I think if you look at the 737 and the A320 airplanes, so A320 has 2 engine options and the 737 only has 1. And so there's a lot of politics in the background about which engine manufacturer gets to play with which airframer. And so I think that's also creating a lot of frustration within the airline industry as a whole.
Well, a lot could change. You look at Boeing's stock sale. A lot could really truly change. And that's a public statement and a public record. I'll put that out there. When you're designing this, do you make clay models? Do you put it in a wind tunnel? Do you do carbon fiber mock-ups? How does it go about when you go about designing the aircraft?
So airplanes are very long-winded programs, making sure that you have discipline and knowing where to allocate capital for development and engineering is very important, especially at the very early stages of the airframe. So usually what happens is we size the airplane in Excel, take out the weights and kind of do basic layouts just to understand what it looks like. And then we start to really focus on something called computational fluid dynamics. And so virtual wind tunnels. And so we have a lot of codes that we utilize surrounding that technology. And it's been really interesting just to watch that technology evolve over the last 15 years. We had to build our own supercomputers back when I was working in the industry. And now everything is on the cloud. So it's very scalable. And so the price of running these simulations has really gone down. But we spent a lot of time in computational fluid dynamics and then, massaging the airplane, as I would call it. Finally, when we have something that really works well, I would say we start to repurpose it into the wind tunnel model world. And so wind tunnel models are brutally expensive. They can cost, between $500,000 up to $1 million just for a model, about a 10th scale model. And it takes 6 to 8 months to build one. It's all custom work. And so then you couple that with the wind tunnel test, which is another, $500,000 to another 1.5 million, depending how much time you're spending there. So the next stage after you get out of the virtual wind tunnel it could cost you $2.5 million in about 6 to 8 months worth of work. But shortly after that, once you have the configuration, then we start moving it into the more traditional CAD, where you actually essentially design the bones of the airplane to fill out the inside, if that makes sense.
A lot of cost, a lot of time, and building an aircraft is very complex. From a simulation perspective, would you have been able to move as fast as you are today with Nautilus if it wasn't for the rapid developments, I'll say, in simulation?
I think, yeah, that's a true statement. I would say so. And the fact that it's in the cloud where, as a startup, you try to do everything you can to not have infrastructure costs, right? And so there's no reason why anybody's setting up server farms right now. So can you use that as a service or, thinking about it that way? And then also with the added, just recently over the last 2 or 3 years, technology of GPUs. And so a lot of the code has moved away from traditional CPUs to GPUs, which has accelerated, the development cycles even further. I mean, I used to need to have 14 to 16 hours to run a single data point, and now I can do it in 2 to 3 minutes. And the difference between that time frame has only been a handful of years. So a lot has changed within the industry.
Are you tapping into accelerators like the Unreal Engine, which is now being used in commercial usage outside of video games?
I think, yes, we are. And so we used things like Unreal Engine to really hook up our technology into a simulated environment. So like you can actually fly our airplane in actually an X-plane or another video game, and it will behave exactly like the real airplane. And so we use the wind tunnel data that I mentioned previously to build all these aerodynamic databases. And then we create our own custom models for aerodynamics and other pieces of it to then hook up into this visualized environment. And so it's a really good way because we can look at data all day long, but then how does the airplane feel? How does the airplane fly? And so those simulated environments that we're using the Unreal Engine are just such an important new tool that you can cross over into to do it. Just as an example, we invite a lot of our airline customers with their pilots. They usually bring their chief pilots along. And so we actually sit them down in front of the computer and we like the simulator. And we say, this is what a 737 would look like. And then they would try to fly it and it's like, oh, it looks traditional. But then we actually flip the picture and say, well, that's actually our airplane. And I know it looks so different, but you've been flying that for the last 10 minutes and the flying and handling qualities are exactly the same.
I've been very fortunate. University of North Florida hosted me. They have a pilot school and they have a simulator, and I went in the simulator. It's hard to fly a plane in the simulator. This is not a walk in the park. This is not Microsoft Flight Simulator with help and cheat codes. This is the real thing. It's really hard. So when you do the virtual testing of your aircraft, and your first aircraft will be the Kona, does it have to meet a certain benchmark then before you'll take it to eventually real world testing? Do you meet a certain milestone in virtual world before you go to test it in physical world?
We do. So airplanes are designed around the code of FAA regulations. And so the airplane aerodynamically has to be able to perform or meet or exceed those types of regulations. And so the virtual work that we do, as well as the wind tunnel work, is all kind of culminated in validating those regulations are met. And that's what creates the high level of safety within the the aviation world today. Unfortunately, it's also one of the things and reasons why airplanes cost so much is that regulatory book is thick and you have to do a lot of work. And you want to make sure that you get that work done ahead of time before real flight testing because the amount of money, let's just say even for our first airplane to run one single hour of flight is, close to $3,000 to $5,000 per hour. And so you want to make sure when you get to that point that everything is dialed in.
Yeah, it's expensive to fly an aircraft. There's a musician I know that has a Gulfstream. It was $7,500 an hour to run his Gulfstream. This was back years ago. I can imagine what it says. So it's very expensive. Your aircraft will have the ability to become autonomous. What impact is that going to have on the cost? Will the cost go down of operating that aircraft when it is autonomous?
Yeah, so we do have the capability in our first product to make it optionally piloted, and that's strictly a freight airplane. And so that airplane has the hooks in it already to do that. When you think about the cost stack of operating an airplane, it's not scalable, so it varies with size and weight. So as an example, if you were to fly a 777 across the Pacific, they have a crew of 3 pilots, but the fuel burn alone is so large that the salaries of the pilots are a really small part of that hourly cost. When you look at the smaller airplanes like the Kona, our first feeder product, that one is, the cost of the pilot is actually quite a bit, it's there, but it's not insignificant as either. So it really comes down to fuel and maintenance at the very end. The autonomy piece allows our customers to do 2 things. The first one is to scale. There's a lot of challenges with the pilots entering the workforce today. And so, especially on the cargo side, they just don't have enough pilots to fly these routes. And so they're thinking that technology is going to allow them to scale up in their operational model. So it's less about the cost, but more about the scalability. And the second thing is, of course, Department of Defense. There's all sorts of new thinking about conflicts and how autonomous or remotely piloted technology will be a really significant portion of this next conflict that's, United States is preparing for.
I was speaking with an individual in DoD yesterday, and you're 100% correct about the autonomy. It's really truly amazing how forward thinking DoD is, and all the various different individual Department of Defense are thinking about autonomy. So when your first vehicle has the ability to operate autonomy, what is the sensors? Do you have to put certain types of sensors? Do you have to put redundant systems? And I know there's less risk because this will be a freight plane, not a human carrying passenger plane. But from a sensor and redundancy perspective, what has to go into it?
So the way that the code is written, the FAA code, is that no single failure can result in loss of flight. And so you do have to have at least dual redundancy. And how you do that is really dependent on the company. But as an example, when you think about autonomy, I think a lot of folks really gravitate towards the autonomous cars. Thinking about a Tesla, it's got all this technology inside of it. It's very visual, uses cameras, maybe a little bit of radar technology in there to really navigate these complex, ever-changing, I would say, street situations, right? But for airplanes, the first flight of an airplane was 1903. First autopilot was 1913. And so that was maybe the first indication of autonomy. So our airplanes are designed to go essentially traverse these highways of the skies, which the FAA or the air traffic control then also monitors. And so there's actually a lot of guide rails around airplanes that don't exist for autonomous car systems. And so our sensor suites are more primitive and they don't cost as much. So it's really gravitating on the radar system as well as something called a detect and avoid system, which is more visual. And so as smaller airplanes and things like that start to navigate the skies, those guys don't have the same sensor suites as we do. So we have to be able to see and then avoid those folks as well. And so that's really, when you think about what goes into that, it's really processing and radar and then also some visual sensors as well. But other than that, short of things like radar altimeters and flight control actuators, which are typically the bane of my existence, is flight control actuators, everything else is pretty simplified when you think about other autonomy systems.
I love that line. Highways of the sky. Now that's clever. So when you get up there, and if you're going through the clouds, there's a thing called weather. And we've all experienced turbulence. Do you have to build in weather sensors or the ability to detect weather or incoming weather into your system?
I think the answer is yes, but it's, honestly, pilots don't rely on that as much anymore. And so I think, before air traffic control, satellite communication, GPS, and all these really fancy infrastructure that we've built out, weather radar was incredibly important. And so the pilots had to make a decision in flight whether they want to, divert somewhere or change heading or climb up a little bit. And so those weather radars became very important. And now with all these complex weather systems that are currently, I would say, installed for just on the ground, for just normal, I would say you and I, there's less reliance on the weather radar inside the airplane. And so you see a lot more, you understand a lot more. And even before you get in the cockpit, you already have a flight plan that takes into account weather. With that in mind, there's certain areas in the United States and the world that weather does change really heavily. And so there is still a lot of things that you have to kind of keep an eye on. But primarily, weather radar is probably the most important piece.
So you have, let's say you have all the components, or you put my chef hat on, you have all the ingredients to make the cake. So you're good there. The first part, as I mentioned earlier, will be the Kona. What type of routes and range are you looking for that Kona? Are you just going to follow traditional air freight routes, or what kind of routes are you looking at for that aircraft?
I think there's two really major use cases that we've kind of found it within our airline customers. The first one is what we call scheduled service. So that'll be for folks like FedEx, UPS, and DHL, typically 1 to 2 hour flights. And the range is about 900 nautical miles. I guess the way I would describe it is from Eugene, Oregon, all the way to Oakland for the FedEx nightly sorts. So connecting smaller regional airports to larger hubs. We found a lot of interesting use cases with other customers that have just these really low infrastructure areas. So like Africa is a good example. Canada connecting the northern indigenous population to the more metro hubs down south, and then island chains. And so, of course, you can't build a road through island chains, and there's no trucking or rail. And so these airplanes, smaller hoppers, actually really help connect a lot of the Oceania regions as well.
So you look at, okay, so I'm putting my geography hat on. This is fun. So if you look at the islands of Indonesia, there's hundreds of islands around Indonesia, Jakarta being the largest, but there's various different islands, and then in that area. And then if you can, I mean, they're closer, but there are some very remote ones in northern British Columbia and Canada. And then if you go from Calgary all the way up to the Arctic, where we do hit the Arctic, you have a remote indigenous population there. Is that type of routes? And then when you go to those routes, you go into regional airports with different types of runways. Will the Kona be able to land in these smaller regional airports?
Yeah, that's the thinking is we have really short field takeoff performance on the airplane. And so we also can land on dirt and gravel as an example as well, which is a very important part if you start thinking about those really remote communities. We had a single customer that I'll tell you an interesting story where he gave us some airports, and I look at the airport, it's really up in northern Canada, and the airport disappears. It depends on the time of day. And we were kind of trying to understand, well, what's going on over there? Well, the airport is actually just a sand beach that has like a really high packed fine sand. And so can you land on sand with absolutely no infrastructure? Those are the types of questions. Then depending on the tides, that sand strip disappears and then it reappears again the next day. But these are the types of, I would say, very unique use cases for an airplane such as the Kona.
How do you engineer from that? So if you're taking apart the engineering stack, you have tires, you have landing gear, and then you have the plating that goes into that for the resistance. And then if you look at sand and weight comes in, we all walk on the beach, foot goes in, but in your case, the tire goes in, gravel stuff goes flying, dirt, it could be muddy, tire goes in. How do you engineer for that?
So there's larger tires is the answer. So you distribute that weight over a larger area. And so that helps kind of, I'm sure if you've been snowshoeing or snowboarding, you kind of understand that concept. That's the first part of it. And the second one is there's a lot of ingestion for like gravel and dirt, as you mentioned. So we have to protect the engine inlets, the propellers, and all these other things that not a lot of people think about for those dirt runway operations.
Do you solve that with coatings, where you put certain types of coatings on the underbelly of the aircraft, or using different materials for that?
So the propellers are the most sensitive. So there's actually special coatings and different, I would say, materials that we use. So there's a lot of push, I would say, in the propeller world for carbon fiber propellers, which are typically lighter, but carbon doesn't do really well for, pebbles hitting it and things like that. And so we had to move to aluminum propellers, which is a little bit more old school, but kind of is able to be more robust. And then, of course, you reinforce the landing gear for the higher loads. And then the underside of the airplane, we put more plies, some more carbon plies to structurally reinforce it, just in case there is a hole that it's not going to create a structural failure inside the airplane.
So you're building, you're building the Iron Man suit around the plane. I'll summarize it that way. Do you feel that these remote environments are your biggest potential market for the Kona, because today they are highly underserved with traditional aircraft design?
I don't think so. I think when you look at the buying power of operators like FedEx, UPS, and DHL in Amazons of the world, that's really where the money is. So, our remote customers will buy maybe like one or two airplanes. So it's a corner case for us. And, it's Alaska bush plane pilots or something. It's a whole different, I would say, way of thinking about it. I think the bulk of our customers for the Kona are in the Department of Defense, as well as these larger carriers that are focused on freight.
The blended wings, it's a fascinating design. You'd look at your traditional tube and wing design. Okay, there's a set of regulatory, this is how you do it, A, B, C, D. We can go down the line. Blended wing, is there a regulatory guide for you to follow, or are you having to work hand in hand with the FAA from a regulatory perspective? So I'll use the term, it's a non-traditional design compared to what's widely available today.
I think that it may seem like that from the outside, but the way that the FAA really approaches certification is based on performance. And so performance is tied to the speeds of the airplane, the weight of the airplane. And so without even showing the FAA what the airplane looks like, if we can hit the same performance numbers for takeoff and landing, as an example, using existing engine technology systems, and then weights are comparable to other airplanes in its class, then I think it really, then you're essentially operating in the same certification base as everybody else, which is the tubes and wings of the world.
So you've got the regulatory framework, you've got the Iron Man figured out, you've got the business model figured out. When do you plan to start initially testing a physical version of the aircraft?
So for us, we built a scale prototype of the Kona, which flew last year in April. That was to validate a lot of our wind tunnel testing. And so that was, I would say a smaller subscale model, but it did show that a lot of our wind tunnel data and the fact that we didn't need a complex autopilot or flight control system actually worked. And so it was really for the first time that we saw something flying in the air that was very indicative of our design. Being an aerodynamicist, I would have to say, for me, the end result is if the wind tunnel shows good, then everything is going to be just fine. And so it doesn't feel like anything is flying in the wind tunnel, but the data coming in is really your indication if you're going to have a successful airplane program or not.
Good data equals good results. So you've tested it, you're going up, and then what happens when you get to commercial level, from a manufacturing perspective? Will you manufacture it yourself? I don't know your world well enough. Are there contract manufacturers that you will go to? How will you ramp up the commercial manufacturing when everything is all checked and ready to go?
It's a good question. It's one of those things that we've been thinking quite a bit as an early stage company. I think there is kind of, I would say, two models right now that have emerged. So as an example, Boeing and Airbus rely on really complex supply chains, and we've seen what that does to the airplane. And so even, within Boeing, if you look at the 60s, 70s, 80s, and 90s, they started to really diversify more and more and more. And so we kind of hit the 787 MAX, not the 787. And then that was, global supply chain, hundreds of partners. And then all of that had to be a really succinct dance show to get everything kind of put together. And that program was way over budget and super late. Then you look at the same thing with an Airbus, where there's so much politics at play, where you have Germany, England, and France, and a little bit of Italy, all trying to make sure that this is creating job growth. And so they, again, diversify the supply chains through the entire Europe. And so that's kind of I would say, what aviation has done today. And then, and I think it's not the best way to go. And then you look at Tesla or SpaceX, where there's a lot of vertical integration. And that's more indicative of 50s and 60s, where you do have that. And so that builds such a, I would say, cheaper, more profitable airplane where you have more control. The problem is you have to build that infrastructure really early on and invest that capital to make sure that you're able to do it. So, as a startup, cash is king always. And so how do you create this hybrid model where we think the SpaceX and Tesla model is the right way to go, but how do you maneuver yourself at the very early days, to get yourself there? And I think what we found out is we relied maybe 2 or 3 key suppliers. Everything else we try to build in-house. Eventually, hopefully, we'll be able to move away from those 2 to 3 suppliers. But right now, we're kind of in a hybrid approach, trying to drive towards that vision of full vertical integration.
It's the right approach. Look at SpaceX and look at Starship. It's amazing. It's really, truly amazing. And you want to look at the Tesla empire, what they're building. I spoke to a CEO of a major, large trucking company, manufacturer, got his hands on a semi. I said, how's your business going to do? And he said, we're effed, beep, 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 beep. And I said, well, why? And he said, they built this thing from the ground up. All we took was an existing chassis, electrified it, and again, insert the beep, 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 beep. And that's coming from CEO of a publicly traded company admitting that to me. It's like, whoa. And so if you're going to take that same approach, yes, it might take you time, and there might be ups, there might be downs. That gives you a massive competitive advantage because you can unlock the cost structure. You can unlock the engineering efficiencies that come with it. In your opinion, so you're going to take that approach. What does the whole future of this blended wing design look like? And as you scale, can we see bigger versions of your aircraft, smaller versions? How do you see that all working out?
Great question. So we always wanted to not only get into the business of one airplane, we wanted to build a family of airplanes. And that was very important for us. And we always knew that the freight sector was going to be our beachhead, but we also wanted to get into the passenger market. And so we just recently made an announcement for our first entrance into the passenger market, which is a narrow body replacement. So that'll be your 737 A320 class. And that is a strictly passenger airplane meant for 200 individuals, which has got range, let's say from New York to London, as well as Denver to Hawaii. And so we were really excited about that announcement. We've already seen a lot of traction within our customer base just to get going on that. And we were really surprised that, the faltering between the duopoly between, of course, the Boeings and the Airbuses of the world has created market opportunities where airlines started to approach us and really ask us, can you adapt to your freighter version, sooner into this market that we're having such a hard time developing? And the narrow body market is so big. Over the next 20 years, there's 40,000 airplanes that need to be built. over the next 20 years, Boeing has the manufacturing capacity for about 10,000 and Airbus 15,000. So that means there's 15,000 airplanes that are completely unspoken for. And as a business owner and a founder, like this is what gets me and my investors really excited. You have this massive market opportunity if you can just break through the capital structure and the technology to get there.
Break that, then it's off to the races. Why would let's say a large international carrier want to use a blended wing design aircraft to move passengers versus a traditional tube and wing aircraft?
Well, I think it's really rooted in the sustainability goals. So a lot of airline CEOs came out over the last couple of years and said we have to be carbon neutral by 2050. Some of them have even more aggressive goals by 2030. And when you think about how to get there, there's only, I would say, two paths. The first one is a sustainable aviation fuel, which everybody, I think, is starting to see the writing on the wall that we just can't develop it quick enough to create that capacity to replace that on a global level. And so when sustainable aviation fuel is not going to get you there, there's, the other option is, of course, well, what can we do with new engine technology? Well, new engine technology, it hasn't really changed. It's been driving a lot of efficiencies, but it hasn't really changed over the last 30 to 40 years. It's still a gas turbine. And so it's just a question of, can you get the materials there, larger turbofans or bypass ratios? Hydrogen has been talked about in the industry for a long time. We're partnering with Zero Avio, which has been a great partner for us. But seems like that's still farther away than we all imagine. And then, of course, the last missing piece, which is where Nautilus comes in, is the blended wing body. So able to reduce with current engine technology about 50% CO2 emissions is what I think gets our customers excited. And doing that in more, I would say, operationally efficient design where you have 30% reduction in fuel. Well, that fundamentally changes the bottom line of these airlines.
We've had Zero Avia on, and they were doing great. You're right. The fuel reduction, another friend of mine, he's former CEO of one of the world's largest airlines. And if I went to him or you went to him, he's retired now, and said, "Sir, we could save you 30% on your fuel," you'd be on the first plane to headquarters. And I can't tell you where headquarters is because you'd be able to figure out what airline that is. From a passenger perspective, if you look at the holidays are coming up, the airlines, they pack them in like sardines. Can we get more individuals on a blended wing aircraft than we can on a traditional aircraft?
Yes, that's the other piece of the puzzle. So one of our advisors, he always says, the 747 was a wonderful airplane because it started out its life as a freighter aircraft and then became a passenger airplane. Whereas if you go the other way around, there's a lot of inefficiencies there. The fact that the DNA of the company is within freights and the blended wing body is such a good freight airplane. There's a lot of, I would say, passenger experiences that you could do. So when you think about the 200 passenger market, we were actually able to get the 200 passengers inside of the airplane and then actually lower the weight of it. And so we are about, I would say 25% less weight than the traditional tube and wing configuration, which opens up even more opportunities with other engine technologies, more, I would say field performance applications as well. And at the same time, the cabin becomes roomier. And so I'm a tall guy, 6'4", and so I've been, hoping for a solution like this for such a long time. And I think this unique configuration offers just a completely different cabin layout, while still maintaining fuel efficiency and performance. So it's almost like a triple threat, which is really great when you think about how well this could perform.
Well, you're giving the carriers options. There's one thing you're not going to have control over, unfortunately, is the leg space. It'd be nice to have an inch or two more, and so you're not crammed in there. I know that's their decision, not yours, but what you're clearly building at Nautilus is you're giving your customers on the freight side, you're giving your customers on the commercial aviation side options, and you're doing that all through blended wing design. I personally can't wait to see blended wings out there flying around, bringing me my next Apple device or taking me on my next vacation. It's really, really exciting. Alexei, as we look to wrap up this insightful conversation for today, what would you like our listeners to take away with them?
It's a great question. So we're always looking for new talent. Obviously, we're hiring right now as we get through our next growth phase. I think it's really interesting to see how the eVTOL space has been, playing out. Obviously, we had the announcement with Lilium, but I also, I think there's a lot of still optimism, both in the investors and customers, about these new aviation and aerospace technologies. And so I think it's really easy to say no to a lot of these things, but it's harder to say yes. But when you make that conviction, that pull to do these new technologies and develop them, I think you'd be surprised at how many other people are excited around you, whether it's investors, customers, and of course your team as well.
If we didn't have new technologies, We wouldn't have a Tesla. We wouldn't have an iPhone. Matter of fact, we wouldn't even have a dishwasher or refrigerator. You always have to develop new technologies and adapt to where the market's going. And that's exactly what Nautilus and Alexei and the team are doing. Today is tomorrow. Tomorrow's today. The future is blended wing aircraft design. Alexei, thank you so much for coming on SAE Tomorrow Today.
Thank you so much.
Thank you for listening to SAE Tomorrow Today. Be sure to join us next week as we explore how sustainable fuel is changing the future of aviation.
SAE International makes no representations as to the accuracy of the information presented in this podcast. The information and opinions are for general information only. SAE International does not endorse, approve, recommend, or certify any information, product, process, service, or organization presented or mentioned in this podcast.